Grounding a sub-panel in a detached garage involves adhering to the National Electrical Code, or NEC, requirements. The code dictates the use of an equipment grounding conductor, or EG, or a grounding electrode system, or GES, for proper grounding. While multiple methods might be acceptable, the preferred approach involves running an EGC from the main service panel to the sub-panel within the garage, in addition to driving a ground rod at the garage location. Let's break down the steps involved. Firstly, install the EGC. This involves running an insulated EGC, typically a bare copper wire, from the main service panel to the sub-panel located in the garage. It is crucial that the EGC is sized appropriately, matching the size of the largest ungrounded conductor present in the feeder cables. Secondly, consider driving a ground rod. Even with an EGC installed, opting to drive an 8-foot ground rod at the garage provides an extra layer of grounding protection, creating an additional path for grounding. Thirdly, focus on the correct installation of bonding jumpers. This includes installing a bonding jumper connecting the EGC and the ground rod, provided the ground rod has been installed. Furthermore, a bonding jumper should be placed between the sub-panel enclosure itself and the ground rod. For the precise location of these bonding jumpers, the jumper between the EGC and the ground rod should be positioned as close as possible to the entry point where the EGC enters the garage structure. The bonding jumper linking the sub-panel enclosure and the ground rod should be situated within the garage, specifically at the point where the sub-panel enclosure is connected to the raceway. Now, let's address acceptable methods of grounding. Running an EGC from the main service panel to the sub-panel while also driving a ground rod represents a sound grounding strategy. Running an EGC from the main service panel, but omitting the ground rod, is another acceptable method. Driving a ground rod alone, without running an EGC, might seem acceptable, but it isn't the preferred methodology. The gold standard remains running an EGC because it offers a more dependable grounding pathway, which enhances safety and performance of the electrical system. Now let's talk about some details about the equipment grounding conductor. An equipment grounding conductor, or EG, is a critical safety component in electrical wiring. Its primary purpose is to provide a low impedance path for fault current to return to the source, typically the main service panel. This low impedance path facilitates the rapid operation of overcurrent protective devices such as circuit breakers or fuses in the event of a ground fault. By quickly clearing the fault, the EGC minimizes the risk of electrical shock, fire, and equipment damage. The EGC is typically a copper or aluminum conductor, either bare or insulated with a green or green with yellow stripes. It is important to note that the EGC should not carry current during normal operation. Its sole function is to provide a safe path for fault current. The NEC specifies the required size of the EGC based on the rating of the overcurrent protective device in the circuit. Proper installation of the EGC is essential for it to function effectively. The EGC must be securely connected to all metal enclosures, equipment, and appliances in the circuit. This ensures that any fault current will have a clear path back to the source, allowing the overcurrent protective device to trip and de-energize the circuit. It's also important to avoid creating ground loops, which can occur when there are multiple paths for ground current to flow. Ground loops can cause unwanted noise and interference in sensitive electronic equipment. In summary, the EGC is a vital safety feature in electrical wiring that provides a low impedance path for fault current, facilitating the rapid operation of overcurrent protective devices. Proper installation and sizing of the EGC are crucial for ensuring the safety and reliability of electrical systems. Now, let's consider grounding electrode systems. A grounding electrode system, or GES, is a network of interconnected grounding electrodes that provide a connection to the earth. The GES is a crucial component of electrical safety as it helps to stabilize the voltage to earth and provide a path for fault current to flow back to the source. This reduces the risk of electrical shock and fire in the event of a ground fault. The NEC specifies the requirements for grounding electrode systems in Article 250. The code outlines the types of electrodes that are permitted, the methods for installing them, and the bonding requirements for connecting them together. Common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, often referred to as UFA grounds. Ground rods are typically made of copper or copper-clad steel and must be at least 8 feet long. They are driven into the ground vertically or at an angle. Ground plates are typically made of copper or steel and must have a surface area of at least 2 square feet. They are buried in the ground horizontally. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements, such as being in direct contact with the earth for at least 10 feet. Concrete encased electrodes consist of a bare copper conductor that is encased in concrete near the bottom of a foundation or footing. The NEC requires that all grounding electrodes be bonded together to form a single grounding electrode system. This is typically done using a bonding jumper, which is a copper conductor that is sized according to the NEC. The bonding jumper must be securely connected to each grounding electrode. The grounding electrode system must be connected to the equipment grounding conductor system at the service equipment. This connection is typically made at the main service panel. In addition to providing a path for fault current, the grounding electrode system also helps to protect against voltage surges caused by lightning or other events. When a voltage surge occurs, the GES helps to dissipate the energy into the earth, reducing the risk of damage to electrical equipment. Proper installation and maintenance of the grounding electrode system are essential for ensuring the safety and reliability of electrical systems. It is important to follow the NEC requirements and to consult with a qualified electrician if you have any questions. The importance of bonding jumpers can't be understated. A bonding jumper is a conductor used to connect metallic parts of an electrical system to ensure electrical continuity and create a low impedance path for fault current. Its main purpose is to equalize the potential between different metal parts, reducing the risk of electrical shock and ensuring proper operation of overcurrent protective devices. Bonding jumpers are used in a variety of applications, including bonding metal enclosures, equipment, and raceways. They are typically made of copper or aluminum and are sized according to the NEC. The NEC specifies the minimum size of bonding jumpers based on the size of the circuit conductors or the rating of the overcurrent protective device. Proper installation of bonding jumpers is crucial for their effectiveness. They must be securely connected to the metal parts being bonded using appropriate connectors and hardware. The surfaces of the metal parts should be clean and free of corrosion to ensure a good electrical connection. It's important to avoid creating ground loops when installing bonding jumpers. Ground loops can occur when there are multiple paths for ground current to flow, which can cause unwanted noise and interference in sensitive electronic equipment. To avoid ground loops, it's important to bond all metal parts to a common grounding point. In addition to bonding metal parts, bonding jumpers are also used to bond non-current carrying metal parts of equipment to the equipment grounding conductor. This ensures that any fault current will have a clear path back to the source, allowing the overcurrent protective device to trip and to energize the circuit. Bonding jumpers are an essential component of electrical safety. They provide a low impedance path for fault current, reducing the risk of electrical shock and ensuring proper operation of overcurrent protective devices. Proper installation and sizing of bonding jumpers are crucial for ensuring the safety and reliability of electrical systems. Now let's look at some NEC references in regard to grounding and bonding. The National Electrical Code, or NEC, contains numerous articles and sections that address grounding and bonding requirements. These requirements are essential for ensuring the safety and reliability of electrical systems. Article 250 of the NEC is dedicated to grounding and bonding. It covers the general requirements for grounding and bonding, as well as specific requirements for different types of systems and equipment. Some of the key topics covered in Article 250 include grounding electrode systems, equipment grounding conductors, bonding jumpers, and methods of grounding. Section 250.4 outlines the general requirements for grounding electrical systems. It specifies that electrical systems must be grounded in a manner that limits the voltage to ground and facilitates the operation of overcurrent protective devices. Section 250.24 covers the requirements for grounding separately derived systems such as generators and transformers. It specifies that these systems must be grounded at the source and that the grounding electrode conductor must be sized according to the NEC. Section 250.32 addresses the grounding requirements for outbuildings in detached garages. It specifies that these structures must have a grounding electrode system and that the grounding electrode conductor must be sized according to the NEC. Section 250.50 covers the requirements for grounding electrode systems. It specifies the types of electrodes that are permitted, the methods for installing them, and the bonding requirements for connecting them together. Section 250.118 lists the acceptable types of equipment grounding conductors. It includes copper wire, aluminum wire, and rigid metal conduit, among others. Section 250.130 covers the requirements for equipment grounding connections. It specifies that equipment grounding conductors must be connected to metal enclosures and equipment in a manner that ensures a reliable electrical connection. In addition to Article 250, other articles in the NEC also address grounding and bonding requirements. For example, Article 300 covers the general requirements for wiring methods, including requirements for grounding and bonding. It's essential to consult the NEC for specific grounding and bonding requirements related to your electrical system. The NEC is a complex document, and it's important to understand the requirements before starting any electrical work. In many jurisdictions, electrical work must be inspected by a qualified electrical inspector to ensure compliance with the NEC. If you have any questions about grounding and bonding, it's best to consult with a qualified electrician. A qualified electrician can assess your electrical system and ensure that it meets the NEC requirements. Now let's address running a new circuit to a detached garage. Running a new circuit to a detached garage requires careful planning and execution to ensure safety and compliance with the NEC. First, determine the electrical load requirements of the garage. This includes calculating the total amperage of all the lights, outlets, and appliances that will be used in the garage. Next, select the appropriate wire size for the circuit based on the amperage load and the distance between the main service panel and the garage. The NEC provides tables that specify the minimum wire size for different amperage ratings and distances. Choose the appropriate wiring method for the circuit. Common wiring methods for detached garages include underground feeder, or UF cable, and rigid metal conduit, or RNC. UF cable is a type of direct burial cable that can be buried underground without the need for conduit. RNC is a type of metal conduit that provides physical protection for the wires. Obtain the necessary permits from your local building department before starting any electrical work. Most jurisdictions require permits for electrical work to ensure compliance with the NEC. Install a grounding electrode system at the detached garage. This typically involves driving a ground rod into the ground and connecting it to the grounding electrode conductor. Run the wiring from the main service panel to the detached garage. If using a UF cable, bury the cable at the required depth and protect it from physical damage. If using RMC, install the conduit and pull the wires through it. Install a sub-panel in the detached garage. The sub-panel will provide circuit breakers for the individual circuits in the garage. Connect the wiring to the sub-panel and install the circuit breakers. Test the circuit to ensure that it is working properly. Use a multimeter to check the voltage and amperage of the circuit. Inspect the wiring to ensure that it is properly grounded and bonded. In summary, running a new circuit to a detached garage requires careful planning and execution to ensure safety and compliance with the NEC. It's important to determine the electrical load requirements, select the appropriate wire size and wiring method, obtain the necessary permits, install a grounding electrode system, run the wiring, install a sub-panel, connect the wiring, test the circuit, and inspect the wiring. Now, let's consider electrical safety tips for detached garages. Detached garages can present unique electrical safety challenges due to their location and potential uses. Here are some important safety tips to keep in mind. Protect outdoor outlets. Use weatherproof covers on all outdoor outlets to protect them from rain, snow, and other elements. Use ground fault circuit interrupters or GFCIs. Install GFCIs on all outlets in the garage, especially those located near water sources. GFCIs are designed to trip quickly in the event of a ground fault, reducing the risk of electrical shock. Inspect wiring regularly. Check the wiring in the garage regularly for signs of damage, such as cracks, frays, or exposed wires. Replace any damaged wiring immediately. Use extension cords safely. Avoid using extension cords whenever possible. If you must use an extension cord, make sure it is properly rated for the amperage load and that it is not damaged. Keep flammable materials away from electrical equipment. Store flammable materials, such as gasoline and propane, away from electrical equipment and outlets. Install smoke detectors and carbon monoxide detectors. Install smoke detectors and carbon monoxide detectors in the garage to alert you to any potential fire or carbon monoxide hazards. Have a fire extinguisher on hand. Keep a fire extinguisher in the garage in case of a fire. Make sure the fire extinguisher is properly rated for electrical fires. Avoid overloading circuits. Don't overload circuits by plugging too many appliances or tools into the same outlet. This can cause the circuit breaker to trip or even start a fire. Be careful when working with electricity. Always turn off the power to the circuit before working on any electrical equipment. Use insulated tools and wear rubber gloves to protect yourself from electrical shock. If you're not comfortable working with electricity, hire a qualified electrician. Electrical work can be dangerous, so it's always best to hire a qualified electrician if you're not comfortable doing the work yourself. In summary, electrical safety in detached garages requires attention to detail and adherence to safety guidelines. By following these tips, you can help to protect yourself and your property from electrical hazards.